Whenever you step inside any structure, you are trusting a silent guarantee that the foundation holding it all together will stay firm, will not split, and will not collapse under immense pressure. For centuries, concrete has been the keeper of that guarantee. From the ancient domes of Rome to massive modern dams, it has shaped human progress across every corner of the globe. We pour billions of tons of this stuff annually, making it the second most used resource on the planet, right behind water. Beating out steel, glass, and plastic by a mile, for the longest time, the world assumed there would never be a better, more affordable substitute. A recent breakthrough out of China has completely flipped that assumption on its head. If you are fascinated by the hidden engineering marvels that are quietly redesigning our modern world, hit that subscribe button, because you will not want to miss how this unfolds. Now, let us dive into the details, because the roots of this shift go way back. To grasp the magnitude of this new material, we first need to look at why standard concrete took over the world in the first place. Grab a chunk of dried concrete, and its nature is obvious. It is cold, rough, and incredibly heavy. It feels more like a piece of the earth itself than a manufactured product. That sheer heaviness is the hallmark of compressive strength, which is the ultimate gold standard in structural design. Standard concrete can easily bear the brunt of 25 to 40 megapascals of downward force without breaking a sweat. Advanced mixes can even push past 100 megapascals. To put that in perspective, 1 megapascal is like stacking the weight of 10 adults onto an area the size of a tiny stamp. Concrete absorbs that extreme pressure effortlessly across millions of projects. For decades, builders rely on it because it is stable, easy to find locally, and can take any shape you pour it into. Suppliers love it because the production methods are dialed in, the workers know exactly how to handle it, and the quality is predictable. And governments rely on it because it is incredibly cost-effective at a massive scale. A cubic meter usually runs around $80 to $120 in major markets, a price that has remained incredibly stable against inflation for years. Nothing else offers that kind of brute strength for that little money. But the reason we haven't fixed concrete's biggest flaw until now isn't because builders were blind to it. We have known since ancient times that concrete hates being stretched or pulled. It has terrible tensile strength. To fix this, the modern world started burying steel bars deep inside it. This steel rebar steps up where the rock-like mixture fails, and together, they built the modern skylines we know today. The catch is that this fix created a brand new weakness the original mixture never had. Steel rusts when exposed to water, road salts, and plain air conditions found in almost every coastal town and snowy region. The metal hidden inside the concrete starts to corrode. As it rusts, the steel swells, blowing the concrete apart from the inside out. This slow destruction, known as spalling, causes most of the world's structural failures. It happens silently, hidden behind concrete walls that look totally fine on the outside for years. In the United States alone, the backlog for fixing broken concrete infrastructure has topped $500 billion. The simple truth is, any steel hidden inside concrete acts like a ticking time bomb, and no amount of tweaking the rebar has ever stopped it. This corrosion is not some design mistake. It is a physics problem born from the materials themselves. For nearly a century, we accepted it because we had no other real choice. The steel inside a pillar does not rust because of bad workmanship. It rusts because nature does not care about human engineering. Salt particles seep through the tiny pores in the concrete, hit the metal, break down its protective coating, and start an unstoppable chain reaction. You cannot just inspect or maintain your way out of this. It is a fundamental clash between the long life that concrete promises and the shorter lifespan that steel forces upon every structure we build. The real-world numbers are specific enough to be alarming. A typical highway bridge in a cold, snowy area will only last about 40 to 70 years before the rust causes serious structural damage. Globally, developing nations burn through over $100 billion every single year just fixing concrete damaged by this exact rusting process. In massive coastal cities like Miami, Jakarta, Mumbai, and Lagos, salty ocean air attacks the steel even faster than winter road salts do. Underwater structures can show serious decay in barely 15 years. This has huge financial and architectural impacts. The rapidly growing tropical and coastal cities that desperately need cheap, long-lasting roads and bridges are the exact spots where steel-reinforced concrete fails the fastest. The very building block meant to make construction affordable for everyone comes with a hidden tax that skyrockets with humidity, heat, and ocean air. For decades, engineers tried to patch the problem. They tried coating the steel in epoxy, using stainless variants, adding electrical protection systems, and mixing in waterproof chemicals. But these just bought a little extra time. They were management strategies, not permanent cures. The big question left on the table was whether a building material could be invented from scratch that simply did not have this fatal flaw, while remaining cheap enough to build cities with. Back in 2018, scientific groups at various universities and government material labs in China started to answer that exact question. They brought forward data that was simply too solid for the industry to ignore. The facilities leading this charge were no small players. Shanghai's Tongji University teamed up with researchers from the Harbin Institute of Technology and the Ningbo Institute of Materials Technology and Engineering. Together, they formulated something they called an ultra-high-performance engineered cementitious composite. Their geographic locations were crucial. Between the salty coastal air of Shanghai, the brutal freezing winters in Harbin, and the heavy industrial capabilities of Ningbo, they had formed the perfect testing triangle for a substance designed to survive any weather extreme. When you finally hear the main concept, it sounds incredibly straightforward. Rather than making up for the poor, stretching ability of concrete by jamming steel into it later, these scientists wondered if the concrete mixture itself could spread out the pulling tension before a crack even had a chance to start. They wanted to achieve this not by making the block harder, but by allowing it to flex slightly and yield gracefully under pressure. Older versions of fiber-reinforced concrete were on the right track, but their execution fell short. Traditional mixes tossed in tiny fibers to stop a fracture from spreading after it had already snapped. That is a reactive approach. The break still happens. The fibers just fight to keep it from getting wider. What these Chinese researchers chased was a proactive method. They fine-tuned the bond between the fibers and the cement so that whenever a stretching force hit, the material would spawn thousands of microscopic, controlled fissures all at once. This spreads the tension throughout the whole block, preventing all that destructive force from piling up at one single weak point. Imagine pulling hard on a pane of glass versus tugging on a fishing net. The glass forces all that pressure into one spot until it shatters. The net, however, shares the burden across every single knot, ensuring no individual thread is ever pushed to its absolute breaking limit. The real genius lay in perfectly calibrating the grip between ultra-thin polyvinyl alcohol fibers, each one finer than a single hair, and the cement holding them. This chemical bond needed to be slightly weak, allowing the fibers to slip just a bit when pulled to trigger that widespread microcracking. But it also needed to be strong enough to pass the physical stress along efficiently before that slipping started. Nailing that exact chemical handshake took 4 long years of trial and error. The end result was something the engineering world had never witnessed. The lingering mystery was how this stuff would actually hold up outside the safety of a lab. And the first thing we need to address about this highly flexible concrete is the one statistic that has sparked the most doubt. When testing standard formulations for shear crushing weight, this new material hits between 40 and 80 megapascals. That is right on par with top-tier normal concrete. It is not magically 5 times stronger under compression. That massive 500% improvement you might hear about refers entirely to its tensile ductility, its ability to stretch without snapping, compared to traditional concrete, which basically cannot stretch at all. Normal mixes snap when stretched by just 1/100th of a percent. This advanced composite, however, can handle being stretched by up to 5% before giving out. That is essentially a 500-to-1 advantage. That specific trait is a game changer because stretching ability is exactly what dictates if a wall will split, flake apart, and let in rusting water. But here is how that data plays out in the real world. For internal metal to rust quickly, a crack usually needs to be at least 1/10 of a millimeter wide, so destructive salt ions can easily get inside. Because this new material absorbs stress through thousands of microscopic fissures, those gaps stay under 6/100ths of a millimeter wide. At that microscopic size, salt intrusion essentially drops to zero. In plain terms, if you build with this high ductility concrete near the ocean, you literally do not need to pack it with steel to keep it from snapping. And when you take the steel out of the equation, you completely eliminate the rusting time bomb. A completely surprising bonus showed up during earthquake simulations. Because this mixture handles extreme stress by forming a web of tiny cracks instead of massive singular splits, it ends up soaking up earthquake shocks with a cushioning effect that standard blocks simply cannot copy. During intense shake table experiments at Tongji University, walls made of this flexible concrete survived violent side-to-side shaking that would have instantly destroyed regular reinforced walls of the exact same size. Even better, they bounced back much closer to their original upright shape. This recovery trait, known as residual drift, is the defining factor in whether a skyscraper is actually safe to enter after a massive tremor. One lesser-known area where this tech is already beating the old standard is in bridge resurfacing. Since this new blend sticks incredibly well to older concrete layers and easily fights off the damage from winter freezing and thawing, real-world highway projects in Jiangsu province are already seeing road surfaces last 3 to 4 times longer than standard paving. The debate was no longer about whether this flexible concrete was functional. The true challenge was figuring out who was going to build the massive supply network needed to pump it out. The leap from the laboratory to the real world did not start with some glamorous skyscraper. It started with a simple highway. In the year 2020, workers repaved a 200-meter stretch of the Shanghai-Chongqing Expressway. They used an advanced overlay created by a startup born out of Tongji University, working alongside regional transportation officials. The road crew used completely normal paving machinery, just tweaking how they mixed the batch. That tiny detail of compatibility would turn out to be the golden key for getting the broader construction industry on board. According to public infrastructure logs tracking the project, after 2 full years of having 12,000 massive trucks roll over it daily, there was not a single, measurable, spreading crack. Standard road coverings on similar stretches usually begin breaking apart in under a year. The real-world results perfectly matched the laboratory hype. It might not seem obvious why real-world proof is so much more valuable than a controlled lab test. A lab eliminates chaos. The actual outdoors embraces it. In a lab, you have perfect temperatures, ideal drying times, and flawless mixing. A chemical mixture might look like a miracle indoors but fall apart entirely on a job site because real building means unpredictable weather, sloppy water ratios, and exhausted crews rushing to beat a deadline. That specific highway test was a huge deal, not just because the durability stats were amazing, which they absolutely were, but because those stats were hit by an everyday road crew dealing with the chaotic logistics of a live construction zone. The head engineer on that project summed it up perfectly, pointing out that their goal was not proving the substance worked under microscopes. The real goal was proving it worked in the hands of regular construction workers. The specific production detail that really caught the industry's eye was how it was mixed. This flexible concrete does not demand any wild new factory machinery. All a plant needs is an accurate machine to drop in the fibers. That small upgrade runs about 80,000 to 150,000 yuan per facility, which is basically the exact same price as adding a normal chemical dispenser. The real-world numbers from that highway project, plus 3 more bridge repavings in Wuhan and Nanjing, were uploaded to China's Open Infrastructure Database in 2022. Engineers all over the world could log in and look at them. It all kicked off with a single project, where lasting a long time was more important than the initial price tag. From there, the idea expanded. The bold claims finally had hard proof backing them up. By 2024, over 340 patent groups are referencing that exact fiber bonding chemistry created by the Tongji, Harbin, and Ningbo teams. We are seeing filings pop up in the US, the European Union, Japan, South Korea, Australia, and Canada. And these are not just polite nods in research papers. These are serious legal and financial bets. Late in 2023, the massive chemical company BASF revealed a licensing deal with a fiber maker in Ningbo. That contract is worth roughly 120 million euros over 5 years and grants them the rights to distribute it throughout North America and Europe. Around the same time, the cement giant LafargeHolcim shared in their sustainability report that they were actively running their own tests on this mixture at 3 different labs, aiming to put a commercial version on the market by 2026. In 2022, the Japan Concrete Institute released an official review, stating that this flexible material passed the strict safety requirements needed for their earthquake building codes. That is a massive regulatory green light, unlocking the toughest, most demanding seismic construction market on the planet. Over in the United States, the Federal Highway Administration threw $18 million at real-world test projects during their 2023 advanced research push. They are testing it in wildly different environments, stretching from the freezing cold of Minnesota all the way down to the humid, salty coasts of Louisiana. But the biggest push speeding up this change globally is actually climate rules. Starting in 2026, the European Union is rolling out a carbon border tax, which means charging money based on the carbon footprint of imported building supplies. Because this new concrete uses industrial leftovers like fly ash and slag to replace some of the traditional cement, it has a significantly smaller carbon footprint for every bit of strength it offers. Whenever a market starts taxing carbon, having a 20 to 35% cleaner building block is not just a passing fad. It becomes a massive financial edge that no major builder can afford to overlook. Because the field data is out in the open for any engineer to read, that transparency has massively sped up global interest over the last couple of years. The China Building Materials Academy safely estimates that if this new concrete replaces just 15% of normal steel-reinforced projects by the year 2040, the money saved on future repairs over the next half-century would top $2 trillion. That is basically the entire yearly economy of Italy, completely wiped from the repair budget and freed up to build brand new structures. Right now, making cement is responsible for about 8% of all global carbon emissions. That is more pollution than all airplanes and cargo ships put together. By swapping in 40% alternative materials, this flexible mix cuts the carbon footprint of every pillar and beam by 25 to 30%. If it reached that same 15% global adoption, we would cut carbon emissions by nearly 200 million tons a year. That is exactly like taking 43 million cars off the highway forever. However, turning a great lab invention into a worldwide standard is a brutal process. We have to be completely honest about where the real hurdles are. These roadblocks are not just imaginary ideas. They are real, trackable issues that need to be laid out just as clearly as the success stories. As of 2024, the whole world only produces about 80,000 tons of the exact fiber this mixture needs each year. To hit that 15% adoption rate by 2040, factories would need to crank out about 600,000 tons every single year. Multiplying production by 7 takes massive amounts of money and a solid decade of scaling up. On top of that, right now this flexible mix is 2 to 3 times more expensive per cubic meter than regular concrete, even over in China. Experts do not expect those prices to match up until at least 2032. Furthermore, building rulebooks in most countries outside of China simply do not have guidelines written for this material yet. Since these rulebooks take 5 to 8 years to update, architects literally cannot use it yet, no matter how good it is. Finally, The entire global labor force only knows how to work with old-school rebar and concrete. Teaching millions of workers a new system takes a whole decade, not just a quick safety meeting. But none of these roadblocks erase the actual science. They just highlight the massive space between what is scientifically possible and what can actually be built globally. Bridging that gap is going to take massive funding, new government rules, and serious teamwork, just as much as it takes good engineering. The scientists behind this breakthrough handed humanity a brilliant new tool. Whether we actually pick it up fast enough to fix our crumbling roads and bridges is another story entirely. The journey of this flexible concrete is really a story about what humans can create and the environments we can build in. For almost all of human history, the buildings a society could create were limited mostly by the materials they had. It was about what they could dig up, what they could afford, and how fast nature would tear it back down. 2 millennia ago, concrete solved a big piece of that puzzle. But the flaw it left behind, the slow, hidden rotting of the metal needed to stretch it, has been draining hundreds of billions of dollars from the global economy every year. And that financial pain hits the poorest nations the absolute hardest. This fairness issue is very real. Places like sub-Saharan Africa, South Asia, and the coasts of Latin America are throwing up buildings fast to shelter booming populations. They are mostly relying on regular steel-reinforced blocks in hot, humid, salty areas where that rusting process happens incredibly fast. An invention that stops that rusting timer entirely without breaking the bank does not just help everyone equally. It provides a massive lifeline to the rapidly growing nations building in the worst weather who simply cannot afford to fix their cities over and over again. That divide is huge, and it will take serious effort to cross. What makes this genuinely revolutionary, not just a tiny upgrade, but a whole new ballgame, is having a building block that survives stretching by bending slightly across its entire surface, instead of standing stiff until it cracks. And it does all of that without a single ounce of steel buried inside. That is not just a small tweak. That is an entirely different level of problem solving. The people who figured this out offered the planet a new way forward. If the world actually grabs onto it quickly enough to fix our decaying cities, is a completely different challenge. That burden falls on politicians, bankers, and factory owners just as heavily as it falls on the scientists. Whenever the foundational building blocks of a society get an upgrade, the benefits do not just add up slowly. They multiply. They pile up with every single bridge built with this mix, every expensive repair job you get to ignore, and every oceanfront town that can now erect structures meant to last 100 years instead of just 40. Concrete is not just a piece of the puzzle. It is the very bedrock of modern life. Shifts at this foundational level take a long time to show up. But once the momentum starts, it is nearly impossible to stop. If the rise of this flexible concrete makes you wonder what other basic materials China is completely reinventing, this time, looking at power grids instead of building sites, there is actually a fascinating answer, and that is exactly what we are covering in the next video. China's fresh take on sodium batteries is about to completely flip the electric vehicle industry upside down. The link between the two is obvious. In both situations, researchers in China are not aiming for expensive luxury products. They are attacking the basic problems of cost and lifespan to make sure this groundbreaking tech is affordable for everyday people. You can find the link to that video down below. If this breakdown shifted your perspective on what our cities are actually built with and how long they are supposed to survive, hit that like button and subscribe for more deep dives into the hidden tech that is changing our world. Ring the bell so you do not miss a single upload, and jump down into the comments to let me know what you think. Now that we finally have a viable, affordable way to beat the rusting concrete problem, what other 100-year-old engineering flaws do you think we are still putting up with, just because nobody has figured out how to make a profit fixing them?